Hello, so these are the solutions for the tryout. And what's it called? I'm gonna try to make as many of the solution videos as I can. Maybe this will be the only one. But yeah, I know it's always nice having the videos because sometimes the written solutions are like, well, where'd they get that from? But yeah, anyways. Okay, first question. It's actually a trick question, kind of. I don't know. Like, you gotta like make sure you read carefully, because this is combinations, right? Not different like orders or permutations, right? It's really easy to say, hey, 3 choices for the first, 3 choices for the second. That's just 9. It's not the answer. And if you put 9, that's okay. Just it's a learning method, so or it's a learning like moment. So basically, think of it this way, right? You could write all of the solutions out. That's pretty straightforward to do because you only have 3 objects. But let's say that we have 2 cases because either the case 1 is they're the same. That means we have 3 different combinations because we have the candy cane, the chocolate bar, and the lollipop, right? The second case is that both are different, right? Right? And how do we figure out how many different ways are there to choose 2 from 3? That's just going to be, we have 3 total things, we're choosing 2. And how do we make sure that this does not like overlap with this at all? Well, those 2 things that you're choosing are always going to be guaranteed to be different. So that's also 3. And then we don't have any other case because either they're the same or they're different. They can't be anywhere in the middle. So 3 plus 3, that's just 6. So yeah. All right. Second one I think was a bit less of a trick question than 1. So basically you got the 6 socks, and essentially this is a good like thing is like number of desired over number of total, right? Right. So basically, what is total is the easiest one to calculate first. You just have 6 socks and you're choosing 2. Those are your entire set of solutions. Desired ones, well, I have 1 case. It's really nice because they get it really nicely given to you, right? This would be the case of the red plus blue plus green, which just is like 2 choose 2 plus 2 choose 2. Like, you know what I'm saying, right? So essentially, like, the nice thing is you just have 1 combination where it's the 2 red socks, 1 combination where it's the 2 blue socks, and then the 1 combination where it's the 2 green socks. So that's just 3. And that's just 3 over 6 times 5 over 2. 6 over 2 is 3, so this cancel with this. Just gives you 1 over 5. All right. So now we have Kevin. Kevin was the name of a roommate I had at a summer camp. That was pretty cool. But yeah. So he flips a coin 4 times. The cases where he gets more heads than tails, if he gets, listen, right? If he gets 2 heads, 2 tails, that's bad, right? If he gets 3 heads, 1 tail, that's good. Or if he gets 4 heads, 0 tails, that's good, right? So for 3 heads, 1 tail, what's the probability of that? Well, it's going to look something like H, 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 T, right? And the probability of each of these is happening is 1/2, so it's just 1/2 to the 4th times the number of ways to order this, which is just technically 4 factorial over 3 factorial times 1 factorial. But better way of thinking of it, you just have 4 places to place the t, so it's just times 4. And so that is just, I'm going to leave it over as 4 over 16. You'll see why in a second. But the reason I'm, actually, I'll just explain it right now. This is because, yeah, basically, like, I know that the other denominator is also going to be 16, but I don't know if it's going to reduce down to something. So I'm just, like, in case I need to add it. Because, yeah, so for the second case, it's just H, 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 H. Pretty easy. That's just 1 over 2 to the 4th. And there's only 1 way to order it. That's 1 over 16. That doesn't reduce, right? So 4 over 16 plus 1 over 16 gives you an answer of 5 over 16. Right. Okay. Now, next solution. This one's actually a nice one. Yeah. Okay. So basically, right? You got this. So I'm gonna actually like break it up into cases, right? Because I immediately see, wow, this is a different right angle than this is a right angle, right? And that I hate like that, right? That like messes with my head. So I'm going to like, because it's like, oh, what do you Like, how do you know like the difference? So I'm gonna have my 9 dots. Case 1 is only right angles like this. Right angles where they're no slopes, like they're parallel to coordinate axes. So yeah, basically, yeah, I have the answers written. I don't think I'm like live solving this. I just have the answers just open, just to make sure I'm like actually like doing the right thing. But yeah, basically, you take this point, right? Let's just look. What are the amount of cases I have? Well, I can have anything. For this to be a right angle, it has to be something like this, right? The reason I'm choosing this point, I'm choosing a point to be a right angle. So I'm choosing this. And now what are the possible like pairs? I could do this and this, right? That would be like something like that. I could do this and that. That would be something like that, right? Essentially, I can either choose 2 of these points and 2 of these points. So I have 2 times 2 pairs for that. Now let's look at another point. I'm going to look at this point now. Same thing. I could choose this one and like have something like this, or I could choose that one. Like, but essentially, I'm in the same position where I have 2 choices for the up and down, and then 2 choices for the left and right. And this one, I could visualize it, or I could realize, hey, this is a square. Something cool about squares is that they're symmetric in not just one way. Like if this is a rectangle, it would be symmetric along this way. So like everything here would be equal to this, but not necessarily the top part. Both squares, it's symmetrical in all 4 ways, and more. But like that's my like main point, right? So therefore, you don't even need to worry about it. Just visualize it like, hey, I'm basically doing the same thing, just mirrored, which means 2 times 2. That with symmetry implies that these 3 are also 2 times 2, right? And you can even play around with it. Take this point, for example, right? I have these 2. I have these 2 pairs. I have these 2 pairs. Essentially, it doesn't matter. And then now the only thing is like for here and here, I'm essentially just doing the same thing. And now I have everything except for the middle point. I'm just going to ask myself if this middle point was it. I can either make something like this, something like this, something like that, right? Essentially, I still have 2 times 2 points, right? So that all is what the case of this. I'm going to call this C1, and I'm going to call this C2, right? Well, everything I just did was C1. Now, let's do C2. I have my lattice grid. Is it called a lattice grid? I know these are called lattice points, but yeah, I have this. Now let's ask ourselves, what does it look like for this? I'm going to call this right angle a 45-degree angle. Why? Because like technically, yeah, it's a right angle, but more so because these are 45 degrees. So basically, okay. First thing is, let's take this point. Can I make a 45 degree? Like, no, I can't, because then it would be like this. That's not a valid one. The only possible right angle is this, and we already calculated that because it has a normal right degree or right angle. So now let's look at this point. I can do this. That works, right? And then also you'll see that you can also do the same thing here. So that's 2 cases. But now, like, remember, symmetry is the big idea here. So if I mirror that, now boom, I have another one, and I have a like. It's kind of hard to see, but like I'm basically doing the same thing just upside down. So I have like one, like I have like one like this. I have another like that, so that's 2. Then I have something like this, and something like this, like an upside down Christmas tree, I guess. That's 2. And then I don't have any more triangles, and you can play around with this in your head, but you shouldn't get any more triangles, right? So now that you already have 2 plus 2, now I'm going to do the same. Now, am I done? No, I'm not, because also if I rotate that square 90 degrees, I'll get something like this. And then I'll also get something like this, right? It's kind of hard to see, but I'll get something like that, and then I'll also get something like that. So that'll just give me 2 more cases. So in total, I have 2 plus 2 plus those other. So that's just plus. I'm just going to say 4 times 2. Why? Because this is a 4 times 9, because I have 9. All of these are 4. So 4 times 9 plus 4 times 2. That just makes up 4 times 11. That is just 44, which is your answer. So yeah. Essentially, split up into casework, and it's not that bad. That's kind of the gist of a lot of counting problems. All right, 5 was also cool because it gets you to think outside the box a little. Like, I know it's less of a probability one, but it is a combination. So I'm going to draw my really cool hexagon. Ew. Okay, so every time you get in this situation, you got to remember that, hey, if I just randomly choose a point here, it's pretty much just going to be fine because it's like, I believe it's called like without loss of generality. Or no, actually, no, that's something different. But it's basically like a thing where it's like you don't need to like worry about if you choose a point arbitrarily and just like pretend all your cases stem off from that case, it'll be fine. So an ant is placed on a corner. I'm just going to choose this corner. Why? Because it's just the most natural corner for me to choose. So how could I possibly get in the same direction after 8 moves? 8 moves is a lot. 8 moves is greater than 6 because 6 sides, that's pretty significant, right? So first thing, okay, I could definitely wrap around and then I would have to hit back one, right? So that's one move. I could do the same thing but in the other direction. So I'm just going to write down cases. So case 1, right, that would just be like right, and then right, and then left. So that would be 7 right. So R, 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 R. And if you see what I'm doing here, the reason I'm writing it, like if you remember, this should look familiar to that one time we did like those, like how many different paths are there problem, right? Because when you like literally think about it this way, right? You only have 2 decisions as your ant. Either you move right or you move to the left, right? 2 different decisions, and it's kind of like, okay, what is the, I should backtrack a little bit actually. I should just ask myself, what is the total? Because it is a probability. So total, right? I have 2 choices for each move. I can either move that way or I can move that way. And I don't know what I'm going to move, but I know that every single possibility, it'll be like I'll have 2 choices for the first one, 2 choices for the second one, etc. all the way up for 8 times. So therefore, total, that's just equal to 2 to the 8th, right? Now I'm going to my desired cases. So I could go right, left. Or I could do the other case, which is just a backward. Just L, 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 R. Now, am I done here? No, because I can think of one more case. I can go like this, go that, and then, I switch around. So like I go like this, and I finally come like that. You know what I'm saying? You have 2 here, 2 here, and then you finish. No, yeah, and then you go around 4, and then you wrap around with 2 again, right? So that's a case. I don't know if that's the only case left, right? So I'm just gonna say, okay, I don't know, like I go right, left. Now notice something. I could literally whip out infinite, or not infinite, but like a lot of cases for this, right? But now I have general cases. Because do I really care about, L, R, L, R, L, R? Like, do I really care about that case? The answer should be no. Because this case stems from this case. Because it's just a combination of case 3. So you're essentially asking yourself, hey, how many ways are there to like I have like a case, right? Is it a unique case in the sense that can I build another one of these cases off from it? No, because case 2 is L, 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 R. There's no other case that has 7 L's and 1 R. And if you play around with it, you'll realize that these are the only fundamental cases you get. So now you are going to ask yourself, okay, well, what is the probability of each of these cases happening? So I guess you don't even have to consider the total if you do it the way I'm about to show you. But for case 1, you're going to be like, okay, the probability for each of these moves is 1/2. And that's nice because that's just 1/2 to the 8th. That's already your baseline probability. Now you're asking yourself, how many different ways are there, right? It's the same thing. Imagine you have coins and you have heads, tails, heads, right? How many different ways? It's 4 choose 1 because you're choosing where the tail to go times 1/2 to the 4th, right? And prove that formula on your own. But that's the same mentality here. Now, how many different ways are there to permute this? 8 factorial over 7 factorial times 1 factorial, right? Figure out why that formula makes sense because we've used it a lot in the past. Or better yet, just ask yourself, okay, I only have 8 places to place that 2, or 8 places to place that L. So it's got to be times 8. Case 2 is very similar to that. In fact, I'm going to go as far as to say it's the same thing. So I'm not even going to bother writing it out because it's literally the same thing, but L's and R's are switched. We can do that because the probability is the same. I'm just going to tack on a 2 It's for 2 times that, and I'm going to change this to case 1 and 2. Case 3 does become a bit different. Case 3, I still have the fact that it's 1/2 to the 8th. But now I'm like, okay, how many different ways are there to order this sequence of letters? There are a whopping 8 factorial over 4 factorial times 4 factorial, right? Why is that? Because remember, you're just arranging letters in the end of the day, right? So yeah. And if you are confused about why I'm like bothering with the combinations, please ask me tomorrow. Like I will I'll explain it in detail because this is a huge thing you need to remember. So now you have case 1 and 2, you have case 3. What do you do when you get cases? You add them. I'm going to add these cases, and I have my trusty calculator out here. Just going to make sure I'm actually writing the right thing. Yeah, so that will get you the answer of 43 over 128, which is the answer. So yeah. Big thing is, do you know how to like permute like this? Like, do you know how to calculate the probability of this sequence? Because like it looks hard, but once you get the sequences down, it's fairly trivial. So yeah, cool problem, but those are all the problems. If you have questions, please DM me on Discord. I will be more than happy to help. Yeah.